Hello everyone, I will be your instructor in this class. So this class is about advances in semiconductor devices. My name is Zubair Akhtar and I will be taking this class. So I just briefly tell you about my credentials. I have completed my PhD in the allied field from Indian Institute of Technology, Kanpur. I have also completed my master's in the same field from Indian Institute of Technology, Roorkee. I have completed my bachelor's programs in electronics as a basic. I just wanted to highlight my research experiences where I work on ADNOC as a research engineer. I work as an assistant professor in BIT Masra. I also involved in various research activities during my PhD program. So those are different than my PhD. Actually, those are some sponsored projects on which we have made some progress. So during the course commencement, if you would like to contact me, so my contact details are as follows. So you can contact me via email or via or via you can visit my office. This is my office location. And if you want to explore more about my profile, you can visit my webpage. So let's begin with this course. So this course is all about analyzing and modeling these semiconductor devices. We'll try to see how these devices can be fabricated and how those devices are characterized. So those characterization parameters later can be used in higher level of designing processes. We'll also try to touch upon the uses of these devices in a complex system. I just wanted to mention here that this course is all about design and analyze. So we'll be toggling about analyze and design phase. I just wanted to make you clear about one reference book, which is Behzad Razavi. You can refer this book, although we will cover a lot of contents from the various research papers, research articles, but I will try to focus on this book because I will try to use the same convention which is proposed or which is basically used in this book. So, I have told too many things about me. I just wanted to ask you about your name and I just wanted to get familiarized with my class. So I would like to do this in a unique way. So suppose I just wanted to perform an activity where I will giving you the two situations, which is the situation one and situation two. So I would like to ask few volunteers of the class who can tell their name and just say one similarity between those two pictures. So I will wait and I will ask so many students during this activity about the similarities. Then I will pause. Then I will ask the differences between these two pictures with the rest of the students. Once they have figured out so many similarities and differences, then I will try to continue in this course as follows. So, oh, we have identified so many similarities and differences, but I would also like to highlight an electronics engineer point of view, where we can see the size of the phone they are using is slightly different. So I just wanted to highlight about the generation gap in the devices where the devices are very long, very big and very bulky to a very compact devices. So how electronics engineers have like transformed these bigger devices to a smaller device. So that kind of challenges we'll try to see in this course and we'll try to figure out how thus this transformation has posed so many challenges in the electronics community. Okay, so we'll try to see how these devices is basically formed. These devices is basically formed of various ICs, and those ICs, the basic building block is the transistor. So if we are talking about a semiconductor IC, then we have lot of semiconductor transistors. So one of that example is here. So once if we are trying to reduce the size of a device overall IC, that means we are trying to reduce the size of a basic building block, which is a transistor. So I will tell how this size transformation is basically has been obtained. So before that, I will try to figure out how transistor look like and how we can minimize the size. So just take an example of like a transistor, the semiconductor transistor MOSFET. So we have seen there is one bulk substrate where we generally put some sort of doping to make, like if this is bulk is p type, then we try to dope with the n type and to make two terminals, which is basically a source and drain. And then there is another terminal which is gate, which is basically insulated by a silicon dioxide layer. So these two terminals are basically directly have an ohmic contact with the substrate, although the gate is not having a ohmic contact with the substrate. It has some sort of silicon dioxide layer, and there is no ohmic contact between this gate terminal and the semiconductor substrate. So how this device work? So suppose if we are not providing any potential, there is no bias. So this is basically, this is p-type semiconductor. So these are the immobility ions, and we have some sort of minority carriers as an electron. Suppose if we apply a positive potential at the gate, so what's gonna happen? Electrons get like attracted by this because of the positive potential, and they get collected at this area. Once this phenomena happens, this is called inversion, and this makes a channel. So this channel is basically is the higher concentration, higher density of electrons in the region where we have a region where we are traveling from drain to source. So this phenomena is called inversion, and this is why we are getting a channel being formed. So we have talked about a channel. So we need to figure out how this channel can be shortened. On what is short channel? So by making a channel short, that means we are making a device little bit smaller in size. So by making a device in little bit smaller in size, that means we can accommodate lot of transistor in the same size, same area, same die area. So the density of these MOSFET, these devices can be characterized as a short channel or a long channel. So we will try to see like how these channels are defined. So this is short channel. We have seen in previous discussion, like we have three terminals. There are two terminals, source and drain, which are basically having a ohmic contact, although we have an insulation layer between gate and substrate. And so once if we define a length which is from, say, the region from source to drain, this is called length and this is called channel length. So if this channel length is having length which is greater than 1 micrometer, it is known to be as, or it is considered to be as a long channel MOSFET. If this distance is less than 1 micrometer, then we talk about this as a short channel. So let's have an activity here. If the channel length of the MOSFET is 2 micrometer, then just discuss amongst your friends and let me know by showing the appropriate color card. This is a color card activity. You can collect your card from here and you can show me the card. with your small group. So if your answer is short channel, then you have to show just me the red card. And if your answer is long channel, then you have to show me the green card so that I can understand how much you have got from this activity. Okay, so let's have another discussion. So why this is so important? We have seen by making this channel little bit smaller in size, we can reduce the power consumption. We can obtain a higher speed, because if the length is less, so our signal can transmit easily and with less time. So high speed can be made. So although there are advantages, there are few issues with these devices. So there are short channel effects which we need to be careful about, which have implications on its threshold voltage, output intermodulation product, and the gain of the device. So now we have seen there are so many kind of short channel effects like channel length modulation, drain induced barrier lowering, hot carrier effect, and body effect. We'll try to discuss those individual effects in detail in the upcoming class. So see you next time and have a good day.